Hello students, so many types of compounds are available. Out of these, many compounds are very much essential for our day-to-day life, for our life existence, for sustainability of life. Some compounds are very much essential. It has very much importance for industrial use and for medical science, we can say, and the composition of our living and non-living matter, basically composition of plants and animals. So some types of compounds are very much essentials. We can say these compounds are complex compounds. These are also called coordination compounds. For example, that we can say chlorophyll is a very much important part of all plants. This chlorophyll, these pigments, mainly it is a complex compound, it is a coordination compound of magnesium, and our body, mainly all living things, animals, mainly contains blood, that is hemoglobin. It is also a complex compound of iron. Vitamin B12, it mainly contains cobalt. So like this, another thing also I can say that for cancer patient we are giving chemo, and chemo mainly it is a complex compound, that platinum, that is called cisplatin, like this. So different types of compounds available. They mainly the compounds of metals, like transition metals, and lanthanides and actinides. If you see, their compounds are very much essential for our day-to-day life. Their existence, their we can say their use are very much importance for our sustainable of life, for life existence, I can say. So today we will discuss regarding the complex compound, that is, it is also called as coordination compound, and how it differ from salt, that is double salt. It is also a compound. How it differ from the double salt, and what are the composition of coordination compound. Today in this lesson we will discuss this thing. So let us start. That coordination compound, it is also called complex compound. Other name, it is also called complex compound. Complex compound, if you see, mainly all complex compound it is made of two parts. If you see, by taking these two things, the complex compound is formed. First one is metal or ion, metal or its ions, and the thing is ligand. These two things constitute complex, constitute coordination compound: metal or its ions and ligand. Basically metals, it may be transition metals, transition elements, or you can say lanthanides or actinides. These are the important metals constitute complex. Another thing, important part of the complex is ligand. Ligands generally, we can say, these are electron donor species. Electron donor species having one or more lone pair of electrons. So, ligands are electron donor species having one or more lone pair of electrons available in it, so that it can donate electrons to the metal atom. Then the combination of ligands and metals always produce metal atom and ligand. Ligand always donates electron pair, lone pair to metal atom, and this bond is called dative bond. So this complex compound is produced due to coordinate covalent bonds between ligands and metal atom or its ions. This coordinate covalent bond produced between the metal atom and ligands forming complex compound. And this, we can say, this complex compound, if you see, for example, I can say one example of complex compound, that FeCN whole 6 K4. K4 FeCN6, it is a complex compound. It is a complex salt. It is a salt. Complex salt. Potassium ferrocyanide. Common name is potassium ferrocyanide. It is a complex salt. It is made of mainly this ferrocyanide ion. This ferrocyanide ion is a complex ion. Its charge is 4 minus and made of potassium plus. 4 potassium plus, and this is cations, and this is an anion. This anion is a complex ion, FeCN whole 6 4 minus, and this combination cyanide and iron produced by dative bond. So once complex compound is produced, the stability of the compound increases, and nowadays these complex compound are very much essential for the existence of our life. All mainly medicines used in the form of complex compound. It is used in the form of complex, and so their existence, their stability is more. So how these compounds, complex compound differ from double salt? We know double salt made of two salts. It is made of two salts. For example, double salt is potassium sulfate, aluminum sulfate, 24 water. It is a double salt made of two salts. And complex salt is made of also two salts. This potassium ferrocyanide is made of potassium cyanide and iron cyanides. If you mix potassium cyanide and iron cyanide, you will get the complex salt, potassium ferrocyanide. And similarly, if you add potassium sulfate and aluminum sulfate, you will get this type of salt, that is called double salt. So what is the difference between double salt and complex salt? If you see their composition and their properties, what are the difference? Double salt also stable salt, complex salt is a stable salt. What is the difference in the physical properties? Let us discuss. If you see, double salt and complex salt. Complex compound are of different types. It may be cationic or anionic. It exists in salt, in form of salt, or may be a neutral species having no charge. It depends upon the nature of compound produced. Double salt, if you see, it is stable. It is stable in solid form. It is stable in solid form and dissociates in water. Double salt is a stable salt in solid form. That is called potassium alum. It is also called potash alum. Potash alum. We are using for antiseptic, for during antiseptic, some substance we use during shaving. So it is a stable salt in solid form and dissociates in water. That means stable in solid form and it dissociates, decomposed in water. But complex compound stable in both solid and in solution. Both in solution form and in solid state, in solid form, in both state it is stable, because it cannot dissociate in water, because this bond, this covalent bond produced between ligands and metal atom is very stable. It cannot be dissociated in water. That's why complex compound is stable in both solid form and in solution. And double salt is stable only in solid form, but when it dissolves in water, it gets divided into opposite charge ions. The constituent particles do not lose the properties. That means when it will be that, for example, potash alum made of potassium sulfate and aluminum sulfate. Potassium sulfate gives potassium and sulfate ion. Aluminum sulfate gives aluminum and sulfate ion. Or when it will be converted to potash alum after mixing potassium sulfate and aluminum sulfate, after formation of potash alum, if you dissolve in water, it gives same potassium ion, sulfate ion, aluminum ion test. So the double salt produced, they do not lose their properties in the in aqueous medium. The constituent ions do not lose their property in solution. That means potassium sulfate, aluminum sulfate, when mixed, you will get potash alum. And potassium sulfate gives potassium ion test and sulfate ion test. And aluminum sulfate gives aluminum ion and sulfate test. But when it will convert it to potash alum, it also gives same potassium ion and sulfate ion aluminum test. That's why the constituent particles do not lose the properties. But very important in complex, they lose their properties. The property loses. For example, potassium ferrocyanide is a mixture of combination of potassium cyanide and ferrocyanide. Both iron cyanide and potassium cyanide, when mixed with definite proportion, then when it is prepared, the complex potassium ferrocyanide, the cyanide ion and ferric ion, this ferrous ion, the ferrous ion and potassium ion remaining same, but in the complex ones produced, it loses the ferrous ion and cyanide ion test in aqueous medium. So when this complex compound will dissolve in water, it cannot produce ferrous ion and cyanide ion because these ferrous ions, cyanide ions, it is already converted in complex form, that is coordinate covalent bond. We know coordinate covalent bond cannot be ionizable, it cannot be dissociated in water. That's why they do not show the test of ferrous ion and cyanide ion in complex. So they lose their properties. Once it is converted to complex form, they loses their properties. So these are the very important difference between double salt and complex salt. Then this double salt and complex salt, if you see the stability, it is also more stable generally compared to, if you see, compared to double salt, it is more stable. And the complex compound, it is also, we can say, it is also more stable. When the complex compound is produced, the stability also increases. But only difference is basis of their properties. They, once it is produced, they do not lose their properties. But once complex compound will be formed, the constituent particle losing their properties. So these are the, another important thing is here, if you see the composition, that the valency of metal shows minimum valency, means original valency. Metal shows minimum valency, that is original valency. It shows original valency. For example, the potassium valency is 1, so it is satisfied. Aluminum valency 3, satisfied. But in complex compound, here generally metal shows two types of valency. One is primary valency, another is secondary valency. Secondary valency always greater than its original valency, and your primary valency indicate that actual valency. This is actual valency and this is secondary valency, that depends upon the coordination, how many number of ligands attached to the metal ion in the coordination sphere. So secondary valency mainly shows the coordination number, CN, coordination number of the metal atom. So two types of valency exist in metal. Two types of valency of metal exist in the complex, but here in double salt, only a single type of valency, only original valency, the actual valency they maintain in the double salt. So for example, I have given the same example. Double salt example is your potash alum, and your complex example you can repeat also same thing, you can repeat later. Potassium aluminum sulfate 24 water is a potash alum, and potassium ferrocyanide is a complex salt. So these are the important difference between double salt and complex salt, and what are the composition of complex compound. Now we discuss, that is types of ligands. You know, the complex compound is made of metal atom or ions and ligands. Ligands are electron donor it is called also Lewis base, having one or more lone pair on the atoms. So these ligands are classified on the basis of, if you see, on the basis of number of donor atoms, on the basis of a number of donor atoms, or you can say how many ligating atoms connected to the metal atoms, that on that basis ligands are. On the basis of donor atom means that is called the denticity. It is also called denticity. On the basis of denticity, that ligands may be monodentate, monodentate means having one donor atoms. Examples: one donor atom, one donor atom, only one atom linked to the metal atom, connected to the metal atom, that is called monodentate ligand. Examples: monoligands are water, OH minus, Cl minus, Cl minus, ammonia. So many types. Examples: water, OH minus, Cl minus, Cl minus, NO2 minus, NO2 minus. So these are called monodentate. Although it has more than one atoms, but at the same time only one atom used as a donor. So these are called monodentate ligand. Only oxygen will be linked to the metal atom. Here oxygen will link to the metal atom. Here either nitrogen, either carbon will use as a, will be connected to the metal atom. So only one atom will be used at the same time. So these are called monodentate ligands. Then didentate. Didentate means two donor atoms are there. Two donor atoms. Two donor atoms. Example: CS2, CS2, NH2. Here two donor atoms. Nitrogen having lone pair. Here nitrogen having lone pair. So it is called ethylene diamine. Short form is EN. Ethylene diamine. EN. 1,2, we can say 1,2 diethylene or ethylene 1,2 diamine. 1, if numbering you do 1, 2 like this. 1,2 ethylene diamine. Ethylene 1,2 diamine. Its short form is ethylene EN. Ethylene diamine. It is a didentate ligand. Similarly, oxalate ion. It is also oxalate ion. It is also didentate or bidentate ligand. Short form is OX. So like this, so many examples: didentate or bidentate. Then tridentate. Here denticity 3, denticity 2, denticity 1, like this. Tridentate example is CS2, CS2, NH, CS2, CS2, NH2, NH2. If you see the structure, here how many donor atoms? 1, nitrogen, 2 nitrogen, 3 nitrogen. So as 1 ethylene, 2 ethylene, so it is called diene, diethylene triamine, diethylene triamine, 1, 2, 3, triamine. Triamine means amine having lone pair on nitrogen, that's why it is called diethylene triamine used as a tridentate ligand. Then tetradentate. Tetradentate ligand, example you can say that CH2 NH, then CH2 NH, then CH2 NH2, here NH2, 1, 2, 3, 4. How many ethylene? 1, 2, 3. So it is called triene. Short form is triene, that is triethylene tetramine, 1, 2, 3, 4. So all amine having lone pair, that's why it is a tetradentate ligand. Triene, diene, only en, like this. Then another one is pentadentate. Pentadentate having 5 donor atoms, short form is you can say like this. Here you see nitrogen having lone pair, here nitrogen having lone pair, and here this is called acetate ion. 1 acetate, 2 acetate, 3 acetate, and 2 amine. Total is 5. So its name is EDTA 3 minus. 1, 2, 3 minus. What is the full form? Ethylene diamine. Ethylene, this is called ethylene. Then diamine, NH, here N, ethylene diamine, triacetate, 1 acetate, 2 acetate, here 3 acetate. So it is called EDTA 3 minus, ethylene diamine triacetate. This is called pentadentate ligand. Then another important ligand is hexadentate ligand. Here denticity is 6. Short form, just I am writing like this, EDTA 4 minus. Here what happens? If we draw the structure, it will be like this: CH2, CH2, N, CH2, CO minus, CH2, CO minus. Here same N, CH2, CO minus, CH2, CO minus. So ethylene, diamine, NN, 2-amine, diamine, tetraacetate, 1, 2, 3, 4. So it is called EDTA 4 minus. EDTA 3 minus is pentadentate and EDTA 4 minus is hexadentate. So on the basis of denticity, number of donor atoms, on the basis of donor atoms, number of donor atoms, number of ligating atoms attached to the metal atom in the complex, these are called denticity, number of donor atoms, monodentate, bidentate, tridentate, tetradentate, pentadentate, hexadentate. So on other cases is called, some ligands are called ambidentate ligand. Ambidentate ligand. What is ambidentate ligand? Ambidentate means monodentate ligand. Monodentate ligand having two donor sites. That means two donor sites means during the formation of complex it can use either one. Examples are Cn minus, either carbon linked or nitrogen linked, CNO minus, CNS minus, NO2 minus. So these are called ambidentate ligand. It can form like this, either M attached to Cn or M attached to NC, like this. When carbon attached to metal atom, it is called cyano. When nitrogen attached to metal, that is called isocyano. So depends upon the atom, the donor atom attached to metal atom. But same types of ligand, Cn, same, formula is same, but the coordination differs. Here carbon is coordinating to metal atom, here nitrogen is coordinating metal atom. Similarly, NO2 also same, you can write like this, M attached to NO or M attached to ONO, like this. So in this case, here N is attached to metal, here oxygen attached to metal. So depends upon the, that means it has two donor sites, either carbon, nitrogen, either nitrogen or oxygen. That's why these are called ambidentate ligand. Then another types of ligands are called chelating ligand. A B C D E, chelating ligand. Which type of ligand are the chelating? Chelating means ring, close ring formation. That is called chelating ligands. How these chelating complexes are produced? Chelating ligands, it produce, that means polydentate ligand, forming chelate, chelates. Chelates means ring, close ring, forming close ring with the metal atom or ion. Polydentate ligand, monodentate ligand cannot forming chelation. Polydentate ligand, more than one donor atoms forming chelates, that is close ring with the metal atom. For example, you can say here copper, then here CH2, that is ethylene diamine, NH2, you can say like this. Then here linkage is like this. Then another CH2, NH2, here CH2, NH2. It is called ethylene diamine, nitrogen attached to copper, and this complex we can say carry, let it be 2+ charge. So this complex, you see, this is forming a chelation. This is forming a chelation, means close ring. So this En, short form is En, it is called a chelating ligand, forming chelation, forming close ring with the particular metal atom. That's why it is called chelating ligand. Then bridging ligand. Another is bridging. What is bridging ligand? Same formation of bridge. Formation of bridge means monodentate ligand having more than one lone pair attached to two metal atoms or ions. That means suppose it is a ligand attached to two metal atoms M1, M2. When ligand attached to two metal atoms, when ligands connected to same ligand connected to two metal atoms, that is called bridging ligand. But this ligand should have more than one donor atom. So we can say more than one lone pair. So one lone pair given to M1, another lone pair given to M2. So this type of complex produced, that you can say this ligand forming a bridge between M1 and M2. This means it is connecting to M1 and M2. That's why it is called bridging ligand. Which type of ligand forming bridging ligand? OH minus, Cl minus, like this, because they have more than one lone pair. That's why they can form bridging complex. So on the basis of that denticity and the nature of ligands, ambident ligands, nature of ring produce chelating complex, and bridge connecting two metal atoms, same ligand connected two metal atoms at the same time, that is called bridging ligand. So different types of ligands are possible. Then important terms used in complex. Already we have discussed ligands, coordination compound, and types of ligands. Already we have discussed. What are the other important terms? First one is coordination sphere. Coordination sphere or coordination denticity in the complex. Coordination sphere. Coordination sphere that indicates metal atom. For example, K4 FeCN whole 6. This is this bracket, this square bracket, the metal atom and ligands combined together is called coordination sphere. Coordination sphere mainly combination of metal atom and ligands. Number of ligands. This constituting the coordination sphere. Central metal atom and number of ligands. Metal atom and number of ligands, both that combination is called coordination sphere. Every complex has coordination sphere. That from coordination sphere we can know how many ligands connected to the metal atoms, how many donor atoms attached to the metal atom, how many ligands or how many donor atoms connected to the metal atom, we can know from the coordination sphere. Generally coordination sphere is written as square bracket. Then what is oxidation number? Number of metal atom. Oxidation number means charge. You can say it is a charge. Charge on metal atom. That is called oxidation number. For example, this complex K4 FeCN whole 6. how much, what is the charge of Fe in this complex. For this 4 potassium, 4 total charge is 4, plus for 1 Fe let it be X, plus 6 cyanide, so that is minus 6 is equal to 0. Charge means we can say oxidation number. The calculation of oxidation number is same method we can apply here. So for 4 potassium 4, iron X, 6 Cn, that is minus 6 equal to 0. So value of X is equal to plus 2. So this is the oxidation number of, that is ON. Short form is ON. ON of Fe in this complex. Then we can say what is coordination sphere, coordination number. Coordination number. Coordination number means that number of donor atoms, but not equal to number of ligands. Number of donor atoms. For example, for this complex FeCN whole 6, if this is a complex ion, this complex ion FeCN whole 6 4 minus, this complex ion, what is the coordination number? Number of donor atoms. Here either carbon or nitrogen can be linked. Suppose carbon, number of donor atoms, only one will be attached. So here 6 cyanide means 6. So coordination number is, here coordination number is 6, because 6 cyanide attached to iron. If you write FeEN whole 3 plus, what is the coordination number? Here you see not equal to number of ligands, always equal to number of donor atoms. En is a didentate ligand, ethylene diamine. As didentate, again multiplied by 3, that is 6. So coordination number is 6, not 3. By mistake, you don't follow the number of ligands. Always follow the number of donor atoms present in the, attached to the metal atom. Here En having 2 donor atoms, so 3, that is 6. So number of donor atoms around iron is 6. So coordination number is 6. So this is regarding coordination number, oxidation number and coordination sphere. Then another thing, some important is term used in the complex, that is Cationic complex. Cationic complex means complex carry positive charge. For example, CO NH3 whole 6, this is a cationic complex. Anionic complex means carrying negative charge. CN whole 6 3 minus. This is a cationic complex, this is a anionic complex. Neutral complex, no charge. Neutral complex having no charge, having no charge. What will be the, for example, CO NH3, CO NH3 3Cl3, this complex. It is a neutral complex, has no charge. Here cobalt, the valence of cobalt satisfied by 3. Charge of cobalt is 3, but it is a neutral complex. No plus and minus is there. No free plus and minus is there. Here it is a free cations. It is a free anions, but it is not a, it has no charge. No, it does not carry any plus and minus charge. Free plus minus charge it does not possess. That's why it is a neutral complex. Then another important term is, next is your homoleptic or heteroleptic complex. Homoleptic means, for example, same example, CO NS3 whole 6 3 plus CO CN whole 6 3 minus. So these are called homoleptic complex. Homoleptic means having same type of ligands. 6 ammonia, 6 cyanide. This is called homoleptic complex. Heteroleptic means different types of ligands. This example, CO NS3 whole 3 Cl3. Other examples, CO NS3 whole CO NS3 whole 2 water, then Br2Cl, like this complex. Here what happens? 2 ammonia, 1 water, 2 bromine and 1 chlorine. Here different types of ligands connected to the metal atom. That's why it is called heteroleptic. Hetero means different types of ligands. Homo means similar types of ligands. That's why on the basis of different nature of complex can be classified. That cationic complex, anionic complex, neutral complex, homoleptic complex, heteroleptic complex, and what are the coordination number, what is the oxidation number, what is the coordination sphere, then what are the different types of ligands. Today we discuss. So next class we will discuss the different nomenclature of the IUPAC nomenclature of the complex. Okay, thank you all.